We have a very interesting session on intention and free will, and we're going to revisit some experiments done decades ago by Benjamin Libet. And first we'll have a full plenary session, and then we will have a panel with 6 short talks, and then a discussion with the 6 panelists and our first plenary speaker, who is, I'm very happy to introduce, Aaron Schurger, from the INSERM Cognitive Neuroimaging Group at the NeuroSpin Research Center, where Stan DeHaan is from as well, in Saclay in France. And he had a recent paper on this in, was it PNAS? In PNAS on this topic that he's going to talk about, which is 50 years without free will. Here you go, Aaron Schurger. Give him a round of applause.
Thank you, and I'd like to thank Stuart and the organizers for a great conference and for inviting me. It's a great honor. Many of the things that you do in a given day are in fact in response to stimuli. For example, the traffic light ahead turns red and you press on the brake pedal. The phone rings and you answer it. Someone calls out to you and you reply. But many, if not most, of the things you do in a given day are done autonomously. There is no stimulus telling you what to do. And this is the question that I've been interested in the past few years, is how the brain initiates actions when there's no cue. So take, for a simple example, you're reading the newspaper in the morning and you have your cup of coffee there. You're not particularly thirsty, but at a given moment, you reach out to take your next sip of coffee. Now, that sounds like a very trivial example. Maybe it's even an insult to free will to think that reaching for your cup of coffee is an act of free will. Although I never feel quite as free as after I've had my morning coffee. Consider this. Why did you initiate that reaching movement precisely when you did and not, say, 200 milliseconds earlier or later? So these are the kinds of questions that keep me up at night. So this, what I call the deciding moment between not moving and moving, for shorthand, I call it the neural decision to move, or the neural decision to act. I use the word decision not in the way that we typically use it, like the decision to go to the grocery store after work. It's an abstract use of the word. So, for example, a neuron, when it fires, has made a decision that its inputs are adequate for it to produce an output. When is the neural decision to act relative to the onset of the action itself? And how is it related to the conscious urge to move? These are the questions I want to take up today. So one of the seminal papers, if not the seminal paper, that started this area of research, at least in modern times, was published more than 50 years ago in 1965 by Kornhuber and Deka. For those of you who don't read German, there you go. They did something that was quite novel at the time. They didn't use any stimulus cues. They let their subjects produce a movement, I think it was just flexion of the wrist, when they wanted to, at sort of odd intervals. And while their subjects were doing this, they recorded EEG. And they discovered what I think many of you are familiar with, the cortical readiness potential. So it's a slow buildup of scalp electrical potential, beginning up to 1 second or even more before the onset of the movement. I don't know if you can see a pointer on the screen. Yes? Okay, yeah. So this is recorded over the motor areas of cortex with EEG, and here, contralateral to the hand that was doing the moving or the foot that was doing the moving, you see this slow buildup. Notice, by the way, that negative is up, and these sometimes it's down and sometimes it's up. Just be sure to watch the labels. So, in spite of years of controversy about precisely what this means, the basic notion that it represents the electrophysiological sign of planning, preparation, initiation of volitional acts. That basic definition has held, or interpretation of the readiness potential has held. And in the interim, the same phenomenon has been observed in single units in premotor cortex of human epilepsy patients, down here by Fried et al. In 2011. And it's also been found in primates, rodents, and even my favorite in crayfish, who have no motor cortex. In fact, they have no cortex at all. About 20 years later, Benjamin Libet, who knew about the readiness potential, was interested in the feeling, or the feeling of having decided to initiate an action, or what he called the urge. He was interested in where in time this urge would be found relative to the time course of the readiness potential. So he recorded EEG while his subjects monitored a clock dial. I suspect this experiment is very familiar to many of you. Subjects monitored this rapidly rotating clock dial, which did 1 revolution every 3 seconds, and were told at odd times to make an abrupt movement spontaneously without any pre-planning. So it says down here, be spontaneous, which is a strange instruction. But oddly enough, subjects are able to do this. They do find it strange at first, but they do it. And I'll come back to that later. So he recovered, of course, the readiness potential. It's very robust, and it appears very reliably when you ask subjects to make movements at their own pace or at a time of their own choosing. What he found that was remarkable and made history was that if you consider the readiness potential to have began somewhere back here, if you can see that pointer, the average time at which subjects reported being conscious of their urge to move was some 300 or more milliseconds later, about 200 milliseconds before the actual initiation of the movement. So this was interpreted to mean in simple terms that we can't possibly have conscious will over our actions. The brain has already decided to produce that movement well before we're even conscious of our own urge or our own intention to produce the movement. So this has given rise to the prevailing view, which I think is still more or less the prevailing view, that what happens back here in time, at about the time that the readiness potential, quote unquote, begins, is some sort of a decision, and all the rest is outcome. And at some point, far down the line, there's the point in time when the self becomes conscious of the decision to move. I would like to offer a new perspective on the interpretation or meaning of the readiness potential by way of a thought experiment. And this is a thought experiment. I didn't do this experiment, but I did actually run the simulations. So imagine that it's flu season and you're doing a study on the etiology of the flu. So you take a large population of people at the beginning of the season and you fit them with one of these wristbands that keeps constant track of their vital signs. Let's say it keeps track of their health points, like in a video game. Okay? So if they get exercise and eat good, then on those days their health points might be a bit higher. If they party too much, drink too much, and get up early, their health points might be lower, and so on. So this is monitoring their health points minute by minute throughout the flu season, and if they should come down with the symptoms of the flu, they're to press a little button, which marks the time of onset of the flu symptoms. And so what we want to do in our study, similar to what we do with the readiness potential, is to take the data epochs from the ones who came down with the flu and align them to the moment at which the flu onset, and examine what happened in advance just before then. So here are just some sample traces from some of the participants who actually came down with the flu. A couple of things worthy of note. One is that we don't have anybody here who didn't come down with the flu. Although there were plenty who didn't, we're not going to study those, right? Because we have nothing to time lock to. Second, notice that their health points are not flat. They wander, they meander around. They're noisy, right? They're not perfectly stable. Of course, at the moment that they come in contact with the virus and come down with the flu, their health points drop precipitously, stay low for a while until they start to get better again. So now let's say that we do, just like we do with the readiness potentials, we find these events, event being onset of the flu, and we align the data to those events and take an average and look and see what happened in advance. So here's the road to the flu. And we see this slow decrease in health preceding the onset of the flu symptoms. This makes sense, that as you're getting the flu, you might get a little bit more and more under the weather gradually, and then really plummet at the end. Now this is a thought experiment, so we know everything. So here's something that we also know, which is that this is the time that they came in contact with the virus. So now, looking at this, something seems really wrong, right? Because if the virus is, contacted with the virus is what gives you the flu, how can you already be getting sicker in advance? Now, one possibility is that the immune system is prescient. It knows that you're going to come down with the flu in a few days and says, well, I might as well get the ball rolling now, right? But we know that something seems a little fishy with that explanation. And the key is to notice that you don't get sick just from getting in contact with the virus. You catch the flu from coming in contact with the virus when your immune system at that moment happens to be ill-prepared to fight it off. So here's one example. A participant who came in contact with the virus many, many times, but only actually contracted the flu when their health score was already on its way down, just randomly, just happened to be on its way down, and that's when they caught the flu. And so, of course, if you time lock to these events, you catch that incidental decline in health that tends to precede getting the flu. It doesn't mean that you were planning or intending to get the flu. So this happens because intrinsic fluctuations in the relevant variable, in this case your health points, get caught in the flash photo of event-locked averaging. And I'm asserting that that's the same thing that happens with the readiness potential, that that's where the readiness potential comes from. Now, are there spontaneous fluctuations in neural activity that could account for this? Absolutely. Neural activity fluctuates constantly, and it looks like this. It looks like this kind of noise here on the top. This is autocorrelated noise, or sometimes called pink or brown noise. It does not look like this. This is white noise. If it looks like this, something's wrong with your equipment, or something's very wrong with your subject. So what makes this noise, quote unquote, autocorrelated is that most of the energy is in the low frequencies, and there's ever less and less energy at higher and higher frequencies. White noise has equal power in all frequencies. So this is the kind of noise we have in the brain. In fact, this is the kind of noise that you have in just about any system in nature, including the weather, and at all spatial scales. So from probability of synaptic vesicle release all the way up to the residuals around your reaction times in a behavioral task. So what got me started with this research was a simple question. How might a machine comply with Libet's instructions? Supposing I was to build a robotic arm that did Libet's task. One easy way to do it would be to take advantage of noise that's inherent in that system. So no matter how much money I spend on my components, I will have some noise at some level in my robotic arm. And so what I can do is I can push up the actuator closer to the threshold and then just wait. And eventually it will cross the threshold by accident because of the noise, and the arm will make a little movement. So this is ultra simple, but it gets the job done. So that's what I started with. And so together with my colleagues, Stan Dahan and Hako Sit, we came up with these two premises. One is that the brain uses the same mechanism for decision-making in a task like Libet's as it would in any decision-making task. That's accumulation of evidence, of neural evidence, up to a threshold. Except in this case, there's no evidence per se. There's mostly internal noise, plus a weak imperative to move. Now, what's this weak imperative to move? You tell your subjects, and I tell my subjects when they come in to do Libet's task, you can make the movement, lifting up your finger, as it happened to be, whenever you want. There are no rules. I'm very explicit about that. And yet, no subject ever waits longer than about 30 seconds to produce a movement. They could, if they wanted to, wait all day. They could never move, and they'd still be complying with the instructions. But because they're in the lab to do an experiment about lifting your finger, somewhere underneath all of that implicit is, move your damn finger sooner or later, right? So that's this weak imperative to move. It's fine. It doesn't kind of ruin the experiment. It just means that it puts some constraints, right? Within a time window of 10 seconds or so, they're roughly free to move their finger whenever they want. And they do. Second premise, when the imperative to produce a movement is weak or absent, the precise moment at which the decision threshold is crossed is largely determined by spontaneous subthreshold fluctuations in neural activity. So here you have this red line represents this weak imperative. It's weak relative to the noise. And you can see that had the noise behaved a little differently, it might have crossed the threshold here. And if the noise had behaved differently here, it might have crossed the threshold, well, off the page, right? So the noise can play a role in crossing the threshold, and since we time lock to supposedly the time of the threshold crossing, then we recover the autocorrelation function of the noise. So this is the model that we used, and compared to some of the math that people have been throwing around in the last couple of days, this is kid stuff. So this is just a simple differential equation. It's called a leaky stochastic accumulator. It has 3 free parameters. Has this drift parameter, which is like this imperative, this weak imperative to move. Has leak, which makes the whole thing more biologically plausible, and a threshold on X. And so this is what, if I run a dozen or so runs of the simulation, this is what the traces look like. They're all superimposed on each other. But basically, it tends to move up a little bit closer to threshold and then reaches stationarity about here, and then just wanders randomly around that point until at some point it happens to cross the threshold. And when it does, I mark the threshold crossing time. And we can look at the distribution of these threshold crossing times. These are analogous to how long the subject decides to wait before making his or her movement. And you can also look at the average trajectory of this decision variable up to the threshold as a surrogate for the readiness potential. And when you do that, when you time lock to these threshold crossings and average together the trajectories, you get something here on the right that looks suspiciously like the readiness potential. So what we did was we fit the distribution of the threshold crossing times to the empirically observed distribution of waiting times and got a really, really nice fit. And then with those very same parameters, we asked, well, how well does the average trajectory fit the readiness potential? And as you can see here, it fit extraordinarily well, up to about 150 milliseconds before the onset of movement. So we wanted to find another way to test our model more formally. And so we thought of the following prediction and experiment to do, which we call the Libet Interruptus experiment. I don't know where that name came from. It just popped into my mind. We were doing the experiment, and that I needed to give the folder a name on my computer where I was keeping the data. So after doing the classic Libet task for about 20 minutes, you repeat the same task again, except every so often there's an occasional click, a quiet little click, and you're told if you hear the click, press the button immediately. Don't wait, as quickly as you can. Otherwise, just keep doing the task as you were. Wait as long as you feel like waiting, and then make a spontaneous movement. So if the click is heard before the movement is made, then the subject has to press the button immediately. That's the bottom line. So consider this simple model of what's happening in such a task. You have a threshold. You have spontaneous fluctuations underneath the threshold. Now, if the interruption happens to arrive here, then the reaction time to that interruption, to that click, will be given by this fast rise, this fast climb up to the threshold. And depending on how far the signal is from the threshold at the time that the interruption happens, your reaction time will be longer or shorter. So if you're interrupted here, your reaction time will be like this. If you happen to be interrupted here, where the signal is already quite close to the threshold, then your reaction time will be that much shorter. And of course, if you made a spontaneous movement, then any interruption after that will never happen. So the prediction is that fast reaction times to interruptions should be preceded by a buildup in negative signal amplitude beginning well before the interruption itself, even when the subject was not preparing to move at that particular moment. And that is indeed what we found to be the case. So I unpack this slide a bit. On the left here, we have the data time locked to the movement, and this is the actual empirical data, and down on the bottom is the model. And on the right, we have the same data time locked to the click. So if you want, you can just focus on the rightmost column, and you can see that there is this slow buildup of electrical potential, nearly linear, for the fast responses to the interrupting click, but not the slow. So this essentially confirmed our predictions. There are a couple of controls that we did. For example, you might say, oh, well, maybe the fast ones were fast just because you happened to interrupt the person at the time that they were getting ready to move. Well, we thought of that in advance, and we told subjects, if you're interrupted and you just happen to be getting ready to move at that moment, say the word coincidence. And so this happened reliably, although rarely, but there were at least a few for each subject, and then we noted those and excluded them from the analyses. So there's some other controls that we did as well, and if you care to, you can ask about them. So our not so prevailing view of the readiness potential is that all of this back here, from about 150 milliseconds before the movement and back as far as you care to go, it's noise. It's spontaneous fluctuations caught in the flash photo of time-locked averaging. And this bit here is a threshold crossing. It's a commitment on the part of the motor system to produce a movement. Before that, no commitment has yet been made. Right? So this is a kind of cute way of summarizing our, say, our hypothesis and why it is what it is. So this is sort of a nod to Lamarck, for those of you who know this debate. So Lamarck saw giraffes. He was interested in evolution, and he said, well, giraffes, the neck gets longer because each generation is stretching and stretching and stretching, and that effort to reach higher and higher leaves somehow gets passed on to the next generation, and the necks get longer. I describe this as sort of a kind of cognitive illusion in the sense of Danny Kahneman. So when you see this readiness potential thing building and building and building, you intuitively get the sense of somebody trying to do something. But of course, as hopefully I've convinced you, that need not be the case. So there's been some recent support for what we call the stochastic decision model in a study on rats by Murakami et al., the lab of Zach Manin. So very, very briefly, the rat waits in a little waiting station. His nose is in this little poke hole, and he hears a tone. The tone says means to wait for a second tone. And when the second tone arrives, that means that the rat can now leave the waiting station and go to a reward port and get a large reward. But the times, the intervals in between the first and the second tone were variable, and sometimes they could get quite long. And the rat was allowed, if he wanted to just leave the waiting station and go to the reward port even before the second tone had happened. But then he would only get a small reward. So sometimes the rat got impatient and just went for the small reward, and they focused on those trials, those impatient trials. And what they found, amazingly, was they were recording from neurons in M2 in the rat, which is roughly analogous to premotor cortex. They found neurons whose activity ramped up to a certain threshold such that when it reached that threshold, the rat initiated his withdrawal from the waiting station and went to get his smaller reward because he had been impatient. Interspersed with those neurons, they found another population of neurons that had a steady, tonic, noisy firing rate that covaried with how long the rat waited before leaving the waiting port. So what it looks like they've identified are a set of neurons that are the inputs to and another set that are the outputs of an accumulator that's being used in a situation where there's no cue. So what they say, and I'll quote them, bounded integration models identify the initial intention to act as the moment of threshold crossing while explaining how antecedent subthreshold neural activity can influence an action without implying a decision. So in summary, the stochastic decision model accounts for the electrophysiological and behavioral variables in Libet's task. And if I had the time to talk about it, I'd also tell you about some evidence that it can account for the subjective variables as well. It argues for a late commitment in spontaneous self-initiated actions of about 150 milliseconds before the onset of the movement. It argues that conscious intention has a meaningful and reasonably accurate relationship with the decision to move. What I didn't mention, but was implicit in what I said, Libet's subjects on average pointed to about 200 milliseconds before the onset of the movement as the time when they made their decision. In fact, Libet's mistake might have been to just not take them at their word. Maybe their brain was trying to tell them something relatively meaningful, that this was a point in time when something interesting happened, that your brain made a commitment to produce a movement. And finally, it suggests that a pre-event buildup may be a general phenomenon rather than a specific mechanism. So this is something that you might expect to find in economic data or weather and climate data. So back to this point about a late commitment to move. If the commitment to move is late, how can we test that? How can we test to see whether or not the commitment to move builds up from far in advance before the movement or happens very near in time to the onset of the movement itself? This was a study I took up in collaboration with Rob Shapire and Mehmet Bazbug at Princeton University. We tried to map the time course of neural activity predictive of impending movement using a machine learning technique called AdaBoost. So what we needed first, though, was some data that had the proper control condition. So I'll get to that in a minute. I'll explain how the experiment worked. Subjects just watched a slideshow with pretty slides, and they advanced the slide at their own pace. Whenever they had had enough of that particular slide, they pressed a button. Just before each slide, there was a cue that said either auto or manual, automatic or manual. If you saw a manual cue, it meant that for this next slide, it was up to you to lift your finger to advance to the next slide. And if the cue said automatic, or auto for short, it meant that you just kept your hands palms down on the table and just waited, and the slide would advance by itself. Now, importantly, the viewing time for these automatic trials was drawn from the subject's own viewing time distribution on these manual trials, so that by the end of the experiment, we had two sets of data, one terminating with a movement and one terminating without a movement. And we could time lock then with these two data sets. We could time lock to the slide transition, controlling reasonably well for things like anticipation and how much time had elapsed. So we did this, and then we asked AdaBoost to try and distinguish automatic from manual trials at each point in time in a sliding window. So this, just to give you an idea of what it looks like from one subject, here in white is the sliding window, which will begin to slide soon. And here is an ROC curve. For those of you not familiar with this is a measure of how well the classifier is distinguishing the two kinds of trial. And when this is pushed up in the upper left-hand quarter, that means you're doing well. So when it's right along the diagonal, it means you are not doing much better than guessing. So here this is. And the question is, does our ability to tell these two apart, to predict whether this was a movement or a non-movement epoch, does its time course look like the shape of the readiness potential, or does it look like something much more abrupt? And if I play this for you again, I think you'll see that it is quite a bit like the latter. So if I stop it right here, you see that it's already, in blue, captured a good portion of the readiness potential, and yet has no real predictive power to speak of. And it's not until really at the very end that this takes off. So this is what it looks like when you average them together. We did this experiment just on 3 subjects, but who came in for repeated sessions so that we had lots and lots of data per subject. What's remarkable about this is that the slow, gradual buildup of the readiness potential, which here it is from the very same data, this is the readiness potential from the same data, is noticeably absent from our ability to tell movement from non-movement trials apart. So what are some of the implications then of this late decision account that I've described? Well, one is that the body may play a role in the decision to initiate movement. Now, typically, we think of the decision to initiate movement as something that happens in the brain, and then it's transmitted to the body. My brain decides, move your right arm, and it sends the signal to my right arm, and I move it. But the late decision account allows for another more interesting possibility, which is that the decision to move is an agreement between the brain and the body, an agreement that's made in a sort of dynamical system sort of way, owing to fast feedback from muscle spindles. Because it is a closed loop, and the feedback from muscle spindles is quite fast. Our model also exposes an important limitation of using movement-locked data epochs in the study of self-initiated movement, which is the main approach that's been used to date. The problem with movement-locked analyses is that they discount the prior probability of whatever you find in the average. So consider trying to learn to predict the onset of rainfall based on only a sample of rainy days. It will be difficult to generalize to an arbitrary set of conditions because very often it does not rain. In fact, right here. Likewise, in the study of self-initiated movement, sampling the conditions that are active when a movement is not about to happen is integral to being able to reliably predict when a movement is going to happen. So some of what we're working on now, and these are no longer really future directions because we've already started, in a way, working on this, is to go from trying to predict what people will do in the future, which is something that's fraught with difficulties and is problematic, to trying to forecast behavior based on brain activity using principles borrowed from meteorology research. So this is the readiness potential seen from a different point of view. So where the readiness potential tells you the probability of the signal at each point in time, given a movement at time 0, this distribution here tells you the probability of movement at times t plus tau in the future, given the state of the system now. And this is just a univariate example of this kind of distribution. It takes a large amount of data to build it up, but we are working with collecting a large amount of data from a smaller number of subjects in the research that we're doing presently. What's important about this is that you can distinguish different kinds of processes. So a deterministic process has its own fingerprint, so to speak, when looking at this kind of distribution. And it's something that you can look at across different species and across different spatial scales, and of course can look at in the multivariate space as well. Here I'm just showing you a univariate version. So I'd like to close just with a simple statement. A single human brain is arguably more complex than the entirety of the Earth's atmosphere. And even the local weather can be challenging to predict, except maybe in Tucson. Yet some have begun to conclude that when it comes to the brain, the game is essentially won. We just put brain data together with machine learning, and we're able to predict behavior. I would submit to you that the game has barely just begun. The self-initiation of action remains a profound mystery. And for those who prefer to believe in free will, in my opinion, there is as yet no hard empirical evidence to stand in your way. Thank you.